solicit questions up to this point. So what we're talking about here is the multipole expansion in electrostatics. And the situation that this applies to is the case in which we have some charge distribution that generates the field that is localized in some region of space. And we then want to ask questions about the nature of the field or the potential when we are observing that far away from the distribution. And when that is the case, then we can take the exact expression for the electrostatic potential and do effectively a Taylor series expansion when the point of observation from the distance from the origin to the point of observation is big compared to the distance from the origin to a point in the distribution for all points in the distribution. Okay? And what we found last time was that we can write that expansion, generally speaking, it will have a term that the potential that is, will have a term that's proportional, falls off like 1 over r. And then the next correction has a term that falls off like 1 over r squared. And then there's a term that falls off like 1 over r cubed, where r is the distance from the origin to the point of observation. And those, the things that are proportional to them are characteristics of the charge distribution. Okay, they're not characteristics of the point of observation. And so we have this thing called Q, a scalar. We have a term that's a vector called P, and a term that was a second order or a rank 2 tensor, capital Q with its devilish hat. This we call the monopole moment, electric monopole moment. This is the electric dipole moment, vector, and then we have the electric quadrupole tensor. We should, indeed, thank you. Okay, so this is a scalar. It's characterized by 1 number. This is a vector. It's characterized by 3 numbers. And let's not think about this more carefully, but at first blush, this matrix is characterized by 9 numbers. Okay? Yeah.
So with a hypothetical octopole, would that be like a 3 by 3 by 3 matrix sort of system?
It would, indeed. And we generally wouldn't write it out as such an object, but indeed it is. Right. Mark, you had a question you wanted to raise?
Actually, I believe you answered it.
Oh, okay. Sorry.
With
heating up the room.
yeah.
Oh, sorry about that. Okay, so physically we were discussing what these things mean. We'll develop that more over the course of this lecture and maybe next. And well, so first thing to think about is if I thought about my charge distribution, if I broke it up into the negative charges and the positive charges, okay? With some distribution function I'm calling n, and I've explicitly factored out the minus sign so that q plus and q minus are positive numbers. Then with this being a normalized distribution function, then the monopole moment is just the net charge. It's the total net charge associated with the distribution. The dipole vector represents something about the position of those charges relative to the origin, so I look at the average position of positive charge weighted by the total amount of positive charge minus the position of the average position of the negative charge weighted by the total amount of negative charge. That's a vector, okay? And if the total charge was net zero, that is, the monopole moment were zero, then this is the familiar form of an electric dipole. It's that charge times the separation vector between the positive charge and the negative charge. Okay. What about this quadrupole? What can we say about this? What is this telling us physically? Well, just to start, this is obviously a much more complicated object with all these different components. A few points, a few properties of quadrupole tensor. Firstly, it's a symmetric tensor. That is to say, if I switch the I and j indices, this is the same thing, right? Secondly, if I look at the trace of the matrix, which is to say I contract the tensor, as we discussed, this notion of contracting indices, setting two indices to be the same, and then summing over the repeated indices. So this is qxx plus qyy plus qzz. Then in this case, for this particular thing, that's equal to 3 times well, I'll just write it out. xi minus 1/3 r prime squared delta I, sum of the repeated indices. Okay? And what is this when I sum this over repeated indices? R prime squared, right? It's the magnitude of x squared, so this is r prime squared. And what is the trace of this matrix? That is to say, the sum of its diagonal elements. 3, right? Because it's 1 on the diagonal. It's the identity matrix in 3 dimensions. So that says this is r squared minus, r prime squared minus r prime squared, which is 0. So the quadrupole is a symmetric traceless tensor, right? And thus, it does not have 9 independent elements because the ones on the off diagonal are related to one another, and the ones on the diagonal have to sum to 0. So if I know qx and xx and qyy, then qzz must be minus the sum of the others. So that means the quadrupole tensor has 5 independent components in general. You might have less if there's other symmetries in the problem. In fact, if we have azimuthal symmetry, we'll see there's only one number that quantifies. When we talk about the quadrupole moment of something, where that's under the context that there's azimuthal symmetry, and there's one number that specifies that. All the others are related, as we'll see in a little bit. What's the physics of what's going on here? So, as I said, the term moment, when we talk about, this is the quadrupole moment or the dipole moment. The term moment in this context is talking about moments of a distribution. When we think about a probability distribution having different moments. So the dipole moment is saying something about the average positions. The quadrupole moment is saying something about the variances in those positions, right? Because it has squares of things. So covariances, if there's, because it's in more than one dimension. Plus, the problem is we have positive and negative stuff, which is makes it life a little bit more complicated than, say, I could talk about the quadrupole moments in gravity too, right? I mean, if I think about gravitational fields, I can also do multipole expansions. Maybe you've done that. Haven't found that negative mass yet, but man, I'm waiting. I was promised a jetpack as a child. I'm not dead yet. All right, so quadrupole moment. Let's just consider the case. Suppose we have only, just for some understanding, suppose we have only positive charge. Okay, so my charge distribution has some total charge Q and some distribution around about whatever chosen origin we have. Okay, what is the nature of the quadrupole moment tensor in that case? So my Qij, let's consider, for example, the moment component Qxx. So that's 3 integral over x primes. Since I only have primes, I'm going to get rid of the damn prime. It doesn't matter. There's only one w variable. I can call it whatever I like. So I have both I and j are equal to 1. So this is equal to this. Okay? And so this is equal to 3 times the average of x squared, average over this distribution. Well, there's the overall charge Q out front. Minus 1/3 the average radius squared. So how shall I think about that? What is that telling me? Oh, no, sorry. Let me in fact, whatever is out there, let me write this. 3q plus, pardon me. Now what is it telling us? Well, suppose we had a spherically symmetric charge distribution. What can we say about things in that context? Well, if we have spherically symmetric distribution, whatever it is, however it is, spherically symmetric, then in that case, the average of x squared equals the average of y squared equals the average of z squared, because it's spherically symmetric. There's no difference in the average variance or position of anything if it's spherically symmetric. I choose the origin at the center. Is that clear? So that means, in this case, average r squared, which is equal to the average of x squared plus y squared plus z squared, is equal to 3 times the average of x squared. Which means if I had a spherically symmetric distribution, then this is equal to 0. In fact, it's true for all of the components. It's obviously true for qyy. It's absolutely true for qzz by adapting the same arguments, by substituting this as y squared or z squared, the argument would go through. And for the off-diagonal elements, it's also true, as you can quickly prove to yourself. So, if I have a spherically symmetric charge distribution, it has no quadrupole moment. So in some sense, what the quadrupole moment is telling us, it's something about how the charges are spread out, because it's this second order moment, but it's saying something about how anisotropically they're spread out. So if I had, you know, a little bit of an oblong-shaped planet, you say that has a quadrupole moment as far as the gravitational field goes, right? Similarly for the charge distribution. So the quadrupole is telling us something about how anisotropic the charges are spread out. Okay. So what about all this other stuff? I mean, so these are just the beginning of, you know, what, getting a little bit of physical intuition about what these different, the properties of the charge distribution relative to the origin. Now, one of the things you're showing for homework is that, of course, the choice of origin does not affect the lowest non-vanishing moment. That's in some sense intrinsic to the distribution itself. It doesn't have to do with the origin. So, I mean, you can kind of see that here in the dipole case. In this case, I chose the monopole moment to vanish, right? Because I have equal amounts of positive and negative charge. So the lowest non-vanishing moment might be electric dipole. And that doesn't depend on the origin, because it depends only on the relative distance, not where the origin is. If this vanished, then the quadrupole moments, its moments don't depend on the origin. But if I had a net charge, then the dipole moment, that vector would depend on the choice of origin. It's one of the things you're studying for homework. All right. So let's just take just a little look at the spatial patterns for the multipole potentials fields. So if I have a monopole, then as a function of position, we have this very simple form. And of course, this is spherically symmetric. So in this case, if I were to plot the equipotential surfaces, of course, they are spheres. And the fields are normal to equipotential surfaces. For the dipole, r hat dot t over r squared, which if I multiply top and bottom by the magnitude r, this is x dot t over r to the fifth, I'm sorry, r to the third, okay, where x is r times r hat. And so I can write this out in terms of Cartesian components if I like, and I like. And I can then, if I want, write this out in spherical coordinates using the relations that everyone must memorize. I don't care if it's open book or not. I'll come and slap your hand if you don't know this. I didn't go to Catholic school, but I have Catholic parents. Okay. In this case, we can just plug these in, and we get this is equal to px times sine theta cos phi over r squared plus py sine theta sine phi over r squared plus the z component cosine theta over r squared. Okay? So these the equipotential surfaces are not spherically symmetric. They depend generally on the angles theta and phi in ways that depend on the different components. Okay? So for example, if I had a suppose that I have only a z component of the dipole moment vector, and the other components were 0, then my equipotential surfaces would vary as a function of theta as cosine theta. So it would be positive for 0 to pi over 2 and negative from pi over 2 to pi. And we would have the usual kind of equipotential surfaces. This kind of surface where I've made this is positive, this is negative. And then we have the fields, which doesn't supposed to be a pure dipole field. It's supposed to be, but it's not because it's going to go like that. Okay? So it's got two poles. It's a dipole. Of course, a physical dipole is two separated charges separated by some amount. At least a physical electric dipole. This is a pure dipole where we're taking the limit that the distance between those charges goes to 0 as the magnitude of the charges increases such that the product of the distance times the charge is a finite number. If I had two physical charges physically separated, as we showed in class last time, there's an exact expression for the potential, which we could do a Taylor series expansion on, and the lowest non-vanishing term would look like that. And if I went really far away from those physically separated charges, I can't see the physical separation, then it would look like that picture. Okay. The quadrupole. Oh, by the way, I should mention, of course, in the monopole, a monopole potential, the potential falls off like 1 over r, the field scales like 1 over r squared, right? Because the field is the gradient of the potential. And similarly here, the potential falls off characteristically with distance as 1 over the square from the dipole, whereas the field falls off like 1 over the cube. for a quadrupole, well, again, this is a half r hat dot q dot r hat over r cubed, multiplying top and bottom by the magnitude of the observation distance squared. This is a half x dot r to the fifth, or 1/2 xi xj over r to the fifth qij, sum over I and j, according to the summation convention. Okay? So let's write this out. Remember that qxy equals qyx. So in off-diagonal terms, you get twice of them, but then with a factor of 2. So this becomes 1 over r to the fifth times x xy qxy plus xz qxz plus yz qyz plus a half x squared qxx plus y squared qyy plus z squared qzz. Of course, qxx, qyy, and qzz are not independent. They must sum to 0. So those are the 5, 1, 2, 3, 4, 5, and this guy depends on 1, 2. And if I wanted to, I can rewrite this in the spherical coordinates, and then I'm going to get sine squared theta sine phi cos phi, which is sine 2 phi over 2, plus 1/2 sine theta cos theta, or 1/2 sine 2 theta cos phi qxz, plus 1/2 sine theta sine phi qyz, plus a half sine squared theta cos squared phi qxx, plus sine squared phi qyy, plus cos squared theta qzz. Blah. Well, this is what it is. We'll get a little bit more intuition about this stuff. But the point is that each component of the quadrupole tensor has a characteristic shape associated with it. In the same way that the electric dipole, in this case we did it on the z direction, had a characteristic shape. There's a characteristic field and a characteristic set of equipotentials associated with that dipole component. And of course, the x and the z are just exactly the same, just rotated by 90 degrees. Here, these different components of the quadrupole tensor have associated shapes as well. In fact, as we will discuss, each of these are related to the components of the spherical harmonics. You kind of maybe see them if you know, if you recognize the spherical harmonics. They're there. These are like second order Y2Ms. These are like the Y1Ms, sort of. I mean, those have I's, and they're like either I plus or minus I, but they're your combinations. I mean, we kind of have a hint of that. Five independent components. Put on 5. No, that's not the 5 I'm thinking of. I'm thinking of the fact that there are 5 independent components for a Y L M with L equals 2, because there are 2 L plus 1 spherical harmonics, right? And at L equals 1, there are 3 components. L equals 0, there's 1 component. L equals 2, 2 times 2 plus 1 is 5. So these different components, as we'll discuss, are related. These shapes of the quadrupole potentials are the spherical harmonics, or something closely related to them. Of course, drawing this right now is kind of a drag, but we can just, in the particular case that we looked at where we had positive charge and negative charge, I mean, we kind of know what the potentials look like, right? There's equipotentials that are kind of like on these, around these different charges. And then you have fields that come out from them, et cetera, with these 4 poles. Vector fields go from positive to negative. But the spherical harmonics will give us a better picture of how to draw these potentials and fields. Okay, so to reiterate a couple of points. The moments of the charge distribution are properties of the charge distribution relative to the origin, generally speaking. Once I know what those moments are, the lowest because of this, let's go back over here. Because of this expansion in terms of powers of 1 over r, the lowest non-vanishing moment dominates. So if I'm very far away from a charge distribution, it's a net charge, it looks like a point charge of charge distribution. If it vanishes, then the next thing I would say, well, if there's unequal amounts of positive and negative charges, if there's equal amounts, so it's 0, but if they're separated in some way, then the next thing I would imagine there would be a dipole moment. And I know, just without any further calculation, this is the form of the potential, and then I can find the form of the field simply as the gradient of that, and all I have to know is what is that moment. And if that vanishes, then I gotta go to this one, oh well, or I might want to make a correction term. So now the question is, how do I actually find what these moments are? Yes?
I was just going to say, what is like the ultimate limit? Like, what is the ultra pole?
We're going to write that down in just a moment.
Okay.
We can write that down. We can write it down both in Cartesian coordinates and spherical coordinates, and we'll do both. It's not that hard. At least you can write it in abstract form. That's not that hard. If you're given a distribution, one thing you can do is just say, let me calculate what the moments of that distribution are. And once I know what those moments are, I can just plug them into this form, and I know what the potential is, and or the field. So let's check. We did a couple of problems on last week on Thursday, where we wrote down the exact potential, at least in some regions of space, and then did a Taylor series expansion on that. Let's do it the other way now. Let's actually find the moments and see if they agree with our Taylor series expansion. So for example, we looked at the problem where we had these 4-point charges, the one that is that ugly picture over there. So here it is again, a little less ugly. On a square, I have a positive charge, a negative charge, and then a positive charge and a negative charge. Where this is the x-axis, this is the y-axis, this the axis is out of the board, and this distance is d. Okay? And everything's on a square. We could write down the exact potential for this trivially, the high school physics problem. We can write down the quadrupole moments. That's not a high school problem. Let's look at really, really good high school. And then I wouldn't say it was good. It made me do that. We want to find the moments of the quadrupole. I mean, because that's the lowest non-vanishing term here, right? In this case, the total charge is 0. Equal numbers of positive and negative charge. So the monopole is 0. What about the dipole vector? Electric dipole moment vector. Well, that represents, in this case, the relative separation of the positive charge compared to the negative charge. But they're both, this one, its average position is the origin, and this one, its average position is the origin. So this is also 0. There's no electric dipole moment associated with this distribution. So we got to go the lowest non-vanishing moment is quadrupole. All right. So in this case, we're, instead of integrating over a continuous distribution, we're summing over a discrete distribution, right? So our moments of the distribution are the sum over all the charges. Now we need some label to label the charge. Let me call it alpha. Times 3, the ith component of the position of charge alpha, the jth component of charge alpha, minus a third, the distance squared from the origin of that charge, delta ij, times the strength of the charge, alpha.
And another third, right? If you bring in the 3.
Yeah. Thank you. All right, so how do we do this? Well, there's a formula here. We gotta pay attention to what all these, we got alphas, we got i's, we got j's, we got q's. Right, this again is about the positions of the charges. That's why I'm not talking about primes versus non-primes. There's one thing here. What are the positions of the charges? So these guys have coordinates. They have coordinates. The position of this charge is d, d, 0, right? X, Y, Z. I don't know. You see what I'm talking about? So, from that, we can see instantly that all of the z coordinates of this are 0. It's in the z equals 0 plane, right? So that means that all the off-diagonal elements with z are 0. right? Because this delta function is 0. Right? This would be equal to just the q alpha times 3 x alpha z alpha for charge alpha. But they all have z equals 0. So this is 0. Is it clear how I did that? Okay. So that's true. Also, what is true is if I look at let's look at qxy. No, I don't want qxy. Well, let's just write it out. So let's look at qxx as an example. Qxx is equal to what do we got? The 3 times the x coordinate of charge number 1 minus this distance squared, which is the square root of 2d, minus 2d squared. That's for charge 1 times q. Then we got q charge 2. It's got a charge minus q. Its x coordinate is the same, and its distance from the origin is the same. Then we have the third guy. The third guy is a positive q. Its x coordinate is minus d, but we got to square it. And its distance from the origin is the same. And we have the last one, which has also a minus x coordinate. Is it clear what I did? Yeah.
I'm confused about the second term there. You have a negative charge q, but
Yeah.
times 3d squared.
So that was
Oh,
3 times
it's-
the x
it's
coordinate
like-
squared.
yeah.
Its x coordinate is also d.
Yeah, so you have negative d and negative.
Yeah.
Gotcha.
So what is qx0 qxx? 0. Similarly, I mean, the y component is exactly the same. We did the same thing. Qyy is 0. So what's qzz? 0. It has to be because qxx plus qyy plus qzz is 0. And qzz is equal to minus the sum of qxx and qyy. And since both of those are 0, we got 0. Well, that leaves us with one thing, and that's the qxy. We kind of, once we get a little bit more intuition about this, we can kind of see that that's the moment that's non-zero because it's got this 45-degree symmetry associated with it. Okay? So what is qxy in this case? Well, I got the first guy. We wrote that down somewhere. It's the sum over the charges. The charge q 3 times the x component of the alpha charge, the y component of the alpha charge. Put these up as superscript stuff. These are not the components. These are just labels for the charges. Okay. So the first charge is plus q. Its x component is d. Its y component is d. Its y coordinate. The next charge is minus q. It has its x coordinate is d. Its y coordinate is minus d. The next charge is plus q. its x-coordinate is minus d, its y-coordinate is minus d, and then finally we have a negative q, its x-component is minus d, its y-component is plus d. And thus, this is a non-zero moment with total quadrupole qd squared. What's the unit of quadrupole? Charge times distance squared. Okay, whatever you want to call that. Right? Monopole is charge, dipole is charge times distance, quadrupole times charge times distance squared. So we could have guessed it's something qd squared. I mean, if you were going to write down something and get a lot of credit, that's what you would say, because you're a good physicist, you see the characteristic scales, there's a q, there's a d, what else could it be? That's the answer, something times qd squared. It's just what that something is. So what is the potential associated with this distribution to lowest order? So for r much bigger than d, when I'm far away from the distribution, then we expect the potential to be approximately equal to, well, in this case, a half xi xj qij over r to the fifth. That's the quadrupole potential that we just wrote down. And there's a qx. This is a half xy plus yx qyx over r to the fifth. But qxy equals qyx because it's symmetric, and thus this is equal to xy qxy over r to the fifth, or 12qd squared xy over r to the fifth, which is what we got when we did the expansion of the exact potential. Now in this case, you could just do that. I mean, you write down the exact potential. It's this trivial thing. It's got 4-point charges in it. But we get a sense of what's going on. Any questions about that? All right, let's look at another problem. The Bernoulli ring of charge. So we looked at this problem last time, where we had, there's no arrow there. Neutral current is a charge. So it's a ring with total charge Q and radius A. And so, when we looked on the z-axis, we could write down the potential exactly, which we did last time, and then we did an expansion when this distance is big compared to the ring. So what did we find? I want to do it again. Yeah, I thought I could have written that down. Right? It should be little q. For this notation that I've chosen here. Okay, so we want to check that that's the same thing we would get if we calculated first the different moments of the distribution, of the charge distribution. So for this case, what is the monopole moment?
charge.
Indeed. Thank you. The total charge Q, which is non-zero. What is the dipole vector?
0.
0. How come?
They cancel.
There's only one charge. Exactly. I mean, there's one charge. If the average position of this charge is the origin. There's no separation between positive and negative charge, and thus the dipole vector is 0. What about the quadrupole? Let's see something here. Right. Okay, so what can we say just from symmetry in this case? This problem is azimuthally symmetric. So, what does that tell me about something like QXY? Well, what is this going to be equal to? This is going to be equal to, in this case, the integral over the circumference, right? The charge, linear charge density here, times the x position of the charge, the y position of the charge, right? Now, in this case, the charge per unit length is a constant. It's uniformly distributed. There's no buildup in one direction of x versus y. You can factor it out. So that's what I mean by azimuthal symmetry. And what is this? Well, dl here is a d phi. That's a little line segment on the arc of the ring. X is a cosine phi. And y is a sine phi. Sorry. We have to get to. All right. So, what is that integral? It's 0, right? I mean, integral of cosine with sine around 2 pi is 0. I mean, we knew that. There's no difference between x and y. It's azimuthally symmetric. So, in this case, this is got to be 0 for azimuthal symmetry. Similarly, in this problem, it's your challenge to show that the off-diagonal components for azimuthal symmetry, for exactly the same reasons, because this thing depends on cosine phi, this thing doesn't depend on phi, this thing depends on sine of phi, this doesn't depend on phi, that because of this, these are also 0 if I have azimuthal symmetry.
You can also argue about that, right?
No. Oh, in this particular case, yes. Yes, in this case. For azimuthal symmetry, that wouldn't generally be true, but you're right. In this case, because it's all in z equals 0, it's obviously true. But it's more generally true. Even if I had a distribution that was a egg, then by azimuthal symmetry, no matter along the z-axis, this is also true.
Couldn't you just use your spherical expansion?
Yeah, that's another way of doing it. It says the same thing. Okay, so we got now all the off-diagonal components, if we have azimuthal symmetry, all the off-diagonal elements of the quadruple tensor are 0. So now we have to think about the diagonal components. Well, if I have azimuthal symmetry, then there's no difference between x and y. That's what it means to be azimuthally symmetric. So these have to be equal because x and y are equivalent. And that thus tells us, in the case of azimuthal symmetry, there is just one number that specifies the whole tensor, and that's qzz. Because qzz plus twice qxx is 0, right? Because qxx plus qiyy plus qzz is 0. And these two are equal, so that tells me that qxx has to be minus qzz. So for azimuthal symmetry, we need one number. qzz, which is sometimes called the quadrupole moment. So if I have an azimuthally symmetric distribution like an egg, we would say there is a quadrupole moment associated with that. And you talk about the nucleus in an atom having a quadrupole moment because of the anisotropy of the nucleons. So what is that one number? In this case, that's equal to the integral around the line of the charge density times 3 times the z component of this thing, which is 0 in this case, because it's on the, as Lewis pointed out, this is at the z equals 0 plane, minus the distance to the origin squared. But all the points are the same distance from the origin. They're a distance a. Therefore, this is minus q squared. Is that clear? These are the coordinates of the charge distribution. In this case, the charge distribution was localized at z equals 0, so I just plugged in that value for z. So, according to our formula, the potential is equal to, the lowest order, it's monopole. And then there are correction terms. And in this case, the only non-zero term is qzz and qxx and qyy. So we have minus a half qxx x squared plus qyy z squared plus qzz y squared z squared over r fifth. And qxx and qyy are equal. They are equal to minus a half qzz. So this is equal to q over r minus a half qzz over 2 r to the 5th times z squared minus a half x squared plus y squared. Where I have substituted in this expression for qxx and qyy. Does this agree with the formula that we wrote down over here? This is only the formula on the z-axis, when the point of observation is on the z-axis. When I'm on the z-axis, x and y are 0. And on the z-axis, r is z. So this becomes, on the plugging in over here, it should have been a plus, shouldn't it? Yeah. Sorry. So I plug in this, minus qa squared, and I get this. All right? Cool. All right. So, let's continue on. So now I'm going to come to Matt's question about what is the most general expansion that we can have? What's its form? To do that, we're going to resort to going back to the Taylor series expansion, writing it out in a more abstract and general way. So, what we want to write down is the general multipole expansion. To do that, the first way we're going to do it is just to write down the Taylor series expansion. So let's recall, if I have a function in one dimension and I'm expanding it in a Taylor series expansion where a is small, then this is equal to f of x plus a times the derivative of f with respect to x at x plus a half a squared, second derivative, etc. So it's the sum over L a to the L over L factorial, the L derivative of f with respect to x at x. And if I have a function in 3 dimensions, well, then I have to think about Taylor series expansions of all 3 components of, that's to say, along x, along y, along z. Again, if this is a small vector compared to this vector, then we can write this out in the same general form. And the 3D generalization of this, which I hope you've seen sometime in your life, doesn't even matter. Okay, so this is just the generalization of this, where we allow the function to be a function of 3 coordinates, or whatever number of coordinates we like. All right? So, here, we consider the function f x minus x prime is 1, or this is really the Green's function. Let me call it that because what the heck, that's what it is. And we're looking at the Taylor series expansion of this, where this is, the length of this vector is small compared to the length of that vector. So we can write down the general form of the expansion. L equals 0 to infinity minus x prime dotted into the gradient, the Lth power of that, over L prime, times the function at a equals 0, which is 1 over the magnitude of x. that's where A equals 0. So this is equal to, we can write out just the first few terms of this. Of course, this is the same thing as 1 over r. So L equals 0, this is 1 over r. Then we have the first order correction to that, which is minus x prime dotted into the gradient of 1 over r. And then we have plus a half of partial I, partial j, I'm sorry, x prime I, x prime j, partial I, partial j, over r. That comes from the second order term. I have two dot products. I have this dot product and that dot product, because L equals 2. Plus blah, blah, blah. Minus 1 to the Lth term, L factorial. There's I1, I2, dot, 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 the Lth moment here, I1, I2, IL, 1 over R. Okay, so this is the Taylor series expansion of the Green's function when I'm far away from the source, when the point of observation is a distance far compared to any position of the source. Okay, now we're going to do some trickery, a whole bunch of it. So these things depend on the coordinates of observation. These things depend on the coordinates of the source. I'm going to call this tensor rank L tensor T. I1, I2, it has L indices. And this outer product has L indices too. I'll call it the polynomial P. P1, I2, up to the L index. All right? Let's take a look at these tensors. In particular, let's look at this tensor. This tensor is symmetric. With respect to interchange of any two indices. Right? Because the derivative, doesn't matter what order I do the derivative. So it's completely symmetric tensor. Moreover, if I contract over any two indices, indices with it, is that spelled right? How is that spelled? Is it IC? Yes. Like that? Thank you, folks. Sorry to see it. Terrible. I'm seeing a horrible example. But, it's just life. All right. So, what can we say? Why is that true? What's true? I just said do it. Well, let's contract over any two. I contract over the first two, it doesn't matter which two I do. Then let's say I contract over index 1 and 2. Then what do I have? When I contract this, what is the result if I sum over the first index?
Laplacian?
Laplacian. Excellent. Because this is del dot del. Also known as the Laplacian. So this is equal to all that other stuff times the Laplacian of 1 over r. And what's the Laplacian of 1 over r for this case? When we're at a point of observation outside the charge distribution. Yeah, exactly. So generally, it's a delta function where the delta function is non-zero where x is equal to x prime. But here, I'm nowhere. I am inside the charge. I'm way away from the charge function. So what's del squared 1 over r? 0. So if I contract over any two indices, the trace over, which is called tracing this, over any two indices is 0. This is a complete, this matrix, or this tensor, not really a matrix, it's generally a high order dealing bob, or thingamajigger. It's completely symmetric, and it's traceless when I contract over any two indices. Such a tensor we call irreducible. We studied this in homework. Everyone got it 100%, so you know this stuff inside out. So these are irreducible rank L tensors. There are two L plus 1 independent components. We will show next time their relationship to the spherical harmonics. But these things, these functions, which are functions of x, y, and z, are called solid harmonics. Having some relation to the spherical harmonics. Now, what the hell is a harmonic anyway? Why are they called spherical harmonics? Does anyone know? Yeah.
They're like waving on a spear or something.
But what does that do with harmonic?
Doesn't it have to do with the harmonic superimpose them all together?
What's that?
You can superimpose them all to get some sort of complex thing.
True, true. So there's some notion of Fourier, maybe some notion of the functions.
Solutions to the Laplace equation?
They are. And but why are solutions to the Laplace equation called harmonic functions? So that is absolutely right. The solutions to Laplace's equations are called, anything that is a solution to Laplace's equation is called a harmonic function. And these are solutions. If I take these t's and I look at the del squared of them, it's 0. Because I put the del squared through, they are solutions to Laplace equations. Solutions to Laplace equations are called harmonic functions. They're called harmonic functions for a very obscure reason, but I thought, what the heck, you call them harmonics? Where did that come from? The reason is because if you do separation of variables of Laplace equation, the Cartesian coordinates, one of the differential equations looks like the simple harmonic oscillator, ODE. Those are harmonic differential equations. That's why they're called harmonic functions. So these are the solid harmonics, and they're irreducible, which means what the important point is what we see here is that this Green's function is when we did this Taylor series expansion, what we find here is that this is the sum over all L times the contraction or the trace of the tensor P with the tensor T, right? Because I'm summing over all of the index indices. I got I1 sum with I1, I got I2 sum with I2, blah, 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 blah. This is an irreducible tensor. And as we know, when you contract tensors, the irreducible pieces pick off the different irreducible pieces. They're like, it's like an orthogonal projection. So this will be equal to the irreducible piece of this contracted with this is already irreducible. Trace. So we only need to, we don't need to just look at the full rank L tensor, we only need to look at the irreducible pieces of that. Those are the kinds of things we see here, like this Qij is looking at the outer product. If I factor out this 3, then you kind of see this is that outer product minus the trace part. It's the irreducible part of that contributes to the solution to the Laplace equation. Because those are the spherical harmonics or the solid harmonics. The harmonics are the solutions to the Laplace equation. And we're looking at the solutions to the Laplace equation because we're looking away from the charge distribution. Okay, to be continued. On Thursday, we will do the spherical stuff. We got some homework that has that too.